When estimating costs for electrical equipment replacement, several factors influence the final price. For a 400 amps fusible disconnect in a NEMA 3 enclosure, the estimated cost ranges from $2,000 to $3,000. This price accounts for the cost of the disconnect itself. For a 600 amps fusible disconnect, also in a NEMA 3 enclosure, the estimated cost is between $3,000 and $4,500. The increase in amperage capacity contributes to the higher cost. When considering a 4-bank meter module with 175 amps, 208 volts, single-phase breakers for each meter, the estimated cost is between $5,000 and $8,000. This module includes multiple breakers and metering components, increasing the overall price. It is crucial to remember that these prices are approximate and subject to fluctuation. The specific equipment manufacturer plays a significant role in pricing. Different manufacturers offer varying levels of quality, features, and brand recognition, all of which impact cost. Labor costs also contribute to the final price. The complexity of the installation, the time required to complete the job, and the prevailing wage rates in the area all influence labor expenses. Local market conditions also affect pricing. Supply and demand, competition among contractors, and the availability of equipment can all cause prices to vary. The provided estimates do not include installation labor costs. Installation can involve disconnecting the old equipment, removing it, installing the new equipment, and reconnecting the wiring. These steps require skilled electricians and can add significantly to the overall project cost. It is important to verify compatibility between the new equipment and the existing wiring and electrical system. If the new equipment requires modifications to the existing infrastructure, this can result in additional costs. To ensure competitive pricing, it is recommended to obtain quotes from multiple contractors. This allows for comparison of different bids and ensures that you are receiving a fair price for the work. The type of disconnect switch being used is another factor to consider. A fusible disconnect switch incorporates fuses for overcurrent protection. The type of fuses used, such as time delay or fast acting, can also affect the overall cost. Non-fusible disconnect switches are also available, and their costs may differ from fusible models. The National Electrical Code, or NEC, provides guidelines for the selection and installation of electrical equipment. Following NEC standards ensures safety and compliance with regulations. The voltage rating of the equipment is crucial. In this case, the meter module operates at 208 volts. Ensure that the replacement equipment is rated for the same voltage to prevent compatibility issues. The amperage rating of the equipment is also critical. The 400 amps and 600 amps disconnects must be appropriately sized for the load they are intended to serve. Overloading the disconnect can lead to overheating and potential hazards. The interrupting rating of the disconnect switch is another important consideration. The interrupting rating indicates the maximum fault current that the disconnect can safely interrupt. Ensure that the replacement equipment has an adequate interrupting rating for the application. The enclosure type of the equipment, such as NEMA 3, is designed to protect against specific environmental conditions. NEMA 3 enclosures provide protection against rain, sleet, and wind-blown dust. If the equipment is installed in a harsh environment, it is important to select an enclosure type that provides adequate protection. The number of poles in the disconnect switch is another factor to consider. A 3-pole disconnect switch is commonly used for 3-phase power systems. The number of poles should match the configuration of the electrical system. The wire size used for the connections is crucial for ensuring proper current carrying capacity. Refer to NEC Table 310.16 for guidance on selecting the appropriate wire size based on the amperage rating of the circuit. The type of wire insulation is also important, particularly in high-temperature environments. THHN and XHHW are common types of wire insulation that are suitable for a wide range of applications. The conduit type used for the wiring can also affect the overall cost. Rigid metal conduit, intermediate metal conduit, and electrical metallic tubing are common types of conduit used in electrical installations. The choice of conduit depends on the specific application and the level of protection required. The grounding of the equipment is essential for safety. Proper grounding helps to prevent electrical shock hazards and ensures that the equipment operates correctly. The grounding electrode conductor must be properly sized and connected to a grounding electrode system. The use of surge protection devices can help to protect the equipment from voltage surges caused by lightning or other electrical disturbances. Surge protection devices are typically installed at the service entrance and at critical equipment locations. The labeling of the equipment is important for identification and safety. The equipment should be clearly labeled with its voltage rating, amperage rating, and other relevant information. The use of arc flash protection is becoming increasingly common in electrical installations. Arc flash protection helps to reduce the risk of injury from arc flash events, which can occur when electrical equipment fails. The coordination of overcurrent protection devices is essential for ensuring that the electrical system operates safely and reliably. Overcurrent protection devices, such as fuses and circuit breakers, should be coordinated to prevent nuisance tripping and to ensure that faults are cleared quickly. The maintenance of electrical equipment is crucial for ensuring its long-term reliability. Regular inspections, cleaning, and testing can help to identify potential problems before they lead to equipment failure. The use of infrared thermography can help to identify hot spots in electrical equipment, which can indicate loose connections or other problems. The training of personnel who work on electrical equipment is essential for safety. Personnel should be properly trained in the safe work practices and procedures for working on electrical equipment. The use of personal protective equipment, or PPE, is essential when working on electrical equipment. PPE can include items such as safety glasses, gloves, and arc-rated clothing. The development of an electrical safety program is important for ensuring a safe work environment. An electrical safety program should include policies and procedures for working on electrical equipment, as well as training and awareness programs for employees. The use of lockout/tagout procedures is essential for preventing accidental energization of electrical equipment during maintenance or repair. Lockout/tagout procedures involve disconnecting the equipment from its power source and applying a lock and tag to prevent it from being re-energized. The use of voltage testers is essential for verifying that electrical equipment is de-energized before working on it. Voltage testers should be used to test all phases of the equipment to ensure that it is completely de-energized. The use of ground fault circuit interrupters, or GFCIs, is required in certain locations to protect against electrical shock hazards. GFCIs are designed to detect small ground faults and to quickly disconnect the power supply to prevent injury. The use of arc fault circuit interrupters, or RFCIs, is required in certain locations to protect against fires caused by arcing faults. RFCIs are designed to detect arcing faults and to quickly disconnect the power supply to prevent a fire from starting. The selection of electrical equipment should be based on a thorough understanding of the application requirements and the environmental conditions in which the equipment will be installed. It is important to consult with a qualified electrical engineer or contractor to ensure that the equipment is properly selected and installed. Consider energy efficiency when selecting replacement equipment. High-efficiency motors, transformers, and lighting can reduce energy consumption and lower operating costs. Check for rebates and incentives offered by local utilities or government agencies for energy-efficient equipment. Proper disposal of all electrical equipment is important to protect the environment. Many components contain hazardous materials that must be disposed of properly. Contact your local waste management agency for information on proper disposal methods. Regularly inspect electrical panels and equipment for signs of corrosion, damage, or overheating. Address any issues promptly to prevent further damage and potential hazards. Keep electrical panels and equipment clear of obstructions to allow for proper ventilation and access for maintenance. Ensure that all electrical connections are tight and secure. Loose connections can cause overheating and potential fire hazards. Regularly test ground fault circuit interrupters, or GFCIs, to ensure they are functioning properly. GFCIs should trip when tested with a GFCI tester. Replace any damaged or worn electrical cords or cables. Damaged cords can pose a shock or fire hazard. Use surge protectors to protect sensitive electronic equipment from voltage spikes. Surge protectors can help to prevent damage to computers, televisions, and other electronic devices. Avoid overloading electrical circuits. Overloaded circuits can cause overheating and potential fire hazards. Be aware of the location of electrical panels and shut-off switches in case of an emergency. Post emergency contact information near electrical panels. Educate occupants on basic electrical safety practices. This can help to prevent accidents and injuries. If you are unsure about any aspect of electrical work, consult with a qualified electrician. Electrical work can be dangerous and should only be performed by trained professionals. The NEC is updated every 3 years. Stay informed about the latest changes to the code to ensure compliance. Local electrical codes may be more stringent than the NEC. Be sure to comply with all applicable local codes and regulations. Obtain the necessary permits before starting any electrical work. Permits ensure that the work is inspected and meets safety standards. Keep accurate records of all electrical work performed, including permits, inspections, and equipment specifications. This information can be helpful for future maintenance and repairs. Consider using a power quality analyzer to monitor the performance of your electrical system. A power quality analyzer can help to identify voltage sags, surges, and other power quality problems. Implement a preventative maintenance program for your electrical system. Preventative maintenance can help to extend the life of your equipment and prevent costly breakdowns. Regularly calibrate electrical test equipment to ensure accurate measurements. Accurate measurements are essential for troubleshooting and maintaining electrical equipment. Use insulated tools when working on electrical equipment. Insulated tools can help to protect you from electrical shock. Wear appropriate personal protective equipment, or PPE, when working on electrical equipment. PPE can include items such as safety glasses, gloves, and arc-rated clothing. Follow lockout/tagout procedures when working on de-energized electrical equipment. Lockout/tagout procedures prevent accidental energization of equipment. Verify that electrical equipment is de-energized before working on it. Use a voltage tester to confirm that the equipment is not energized. Be aware of the potential hazards of working with electricity. Electricity can be dangerous and can cause serious injury or death. Never work on electrical equipment when you are tired or distracted. Focus on the task at hand and avoid distractions. If you are unsure about any aspect of electrical work, stop and ask for help. It is better to be safe than sorry. Remember that working with electricity requires knowledge, skill, and caution. If you are not qualified to perform electrical work, hire a qualified electrician. When evaluating a 4-bank meter module replacement, the physical size and mounting configuration of the new module must match the existing installation to avoid costly modifications. Confirm the availability of replacement parts for the chosen equipment to ensure long-term maintainability. Check the warranty terms offered by different manufacturers to protect your investment. Consider the environmental impact of the new equipment. Choose energy-efficient and environmentally friendly options whenever possible. Evaluate the life cycle cost of the equipment, including purchase price, installation costs, operating costs, and maintenance costs. Choose the equipment that offers the best value over its entire lifespan. When replacing a fusible disconnect, verify the correct fuse type and ampacity for the protected circuit. Using the wrong fuse can lead to equipment damage or fire. Ensure that the disconnect switch is properly labeled with the circuit it protects. This helps to prevent accidental disconnection of the wrong circuit. Inspect the disconnect switch for signs of corrosion or damage. Replace any damaged or corroded components to ensure reliable operation. Test the disconnect switch regularly to verify that it is functioning properly. A faulty disconnect switch can fail to interrupt the circuit in the event of a fault. Use a torque wrench to tighten electrical connections to the specified torque values. Over-tightening or under-tightening connections can lead to overheating and potential fire hazards.